right, everybody. So good afternoon. Thank you all for coming, and thank you for our conference organizers. I'm a community organizer myself, and I know how much time and effort goes into kind of nerd herding. It's a lot of work. So really, thank you to Progress, and special thanks to Brian, who nerd herded me as well and invited me to speak. So my name's Amel Hussein. I'm a senior open web engineer at Boku. We're an open source web consultancy. Our company kind of started out of the jQuery core committer team many, many years ago. We've probably, I'm sure many of you probably used things that have come out of our company or software that we've contributed to, everything from Grunt to Webpack, Babel, JavaScript engines, and now, patching browsers. We're really focused on web interoperability, meaning, how should things work across different browsers. And so a couple of projects that we're really heavily involved with is web platform tests. It's an open source project that Chrome and Firefox and, pretty much all the browser vendors are either using or contributing to, where they get to share their tests. And the goal of that is to have better web interoperability. Another project that we're really involved in is Test262, which tests JavaScript, the language, right? So all these different JavaScript parsing engines, making sure that they're implementing the new specifications of JavaScript the same way. So really exciting stuff. And the web is definitely getting better. Do you guys all agree? Yes? Awesome. No more Netscape days. No DOM wars. So a little bit about me. So I love unit testing, love infrastructure. I'm a co-host of the Web Platform podcast. I'm local to Boston, and so I'm the organizer for the Cambridge Google Developer Group. I think Boston is also the best city in the country, so sorry all other cities. So another really big thing about me, anybody who knows me knows I love the web. I seriously love, I have the web is in my job title, right? I'm an open web engineer. And the web platform is I think the greatest thing we've ever made. But it's also kind of a super hostile environment to develop for, right? So how many web developers do I have in the room? Awesome, mostly web developers. So you guys know that you have the hardest job on earth, right? You have shifting dependencies, shifting targets, everything is moving all the time. It's amazing that things work. All of these challenges, right, and this rapid kind of pace of innovation kind of comes at a cost, right? We have these pretty serious code bases that are pretty large code bases that maybe aren't kind of adapted to modern, kind of our modern lifestyles and some of the tools that we've adopted, right? So I personally think that this little pivot here that happened in 2014 where, for the first time, more people were accessing the internet through their phones than hardwired desktop devices. I don't think we haven't really kind of caught up to that big tipping point. And when I say that, I mean that if you look at the JavaScript that we're kind of pushing forward on the web, the average, this is from HTTP Archive. It's a great site that indexes a bunch of, that kind of indexes the web and puts metrics on, JavaScript payload sizes, what people are using in their code, et cetera. It's pretty cool. And so, the average size of a JavaScript file that we're sending is 415 KB, and that's pretty bad because that's on average over at least 15 seconds or more for a page to get interactive on mobile. And so we're designing our web applications for hardwired desktop devices. We're not really doing a good job of kind of breaking up our code, modularizing it for mobile. And so just to kind of query the room here, and don't worry, we're not going to talk to your bosses or anything. How many of you guys are happy with your code bases? And you can close your eyes, but if you want to raise your hands, how many of you are super proud of your code and you're yeah, I love my code, so happy with it. Oh my God, okay, please, do you work with other engineers? Yeah, native script, okay, got it, all right. So, but so I didn't see a lot of hands go up, and the reality is a lot of us are a little, we have crufty, large code bases, and I think that's totally fine. Like legacy, real applications are living and breathing, and that means that they're gonna have weird parts, and they might be written in 3 different languages, and that's okay. It's how you manage the cruft and how you push your code base forward that really counts, right? So nobody should ever be embarrassed about weird code or their legacy code that they're not happy about. And so my talk is really kind of a plea for better kind of prioritization of maintaining our applications. We're constantly adding features. We're constantly, feature happy. But I don't think we have a culture of really embracing maintenance and really thinking about how we refactor our code. It's just not something that we're like almost like children in a little store. We're like new thing. I don't want the old toy that's at home. But the reality is, like most of us are kind of getting to a stage where we're getting crippled by our code. I'm at Boku. We're open web consultancy. We have pretty big clients, and it's kind of like a common theme across the board that tech debt is going to kind of come back to bite you. It's just a matter of when, right? And so how do we kind of, as developers, how do we deal with managing our tech debt and pushing the web forward while still being able to deliver value? And I think there's a really one of the things that we're going to talk about today is like some tools that will help us kind of move our code base forward. But if we look at some of the common maintenance dilemmas that we face as developers, it's code cruft, it's like lack of conventions, right? It's aging and shifting dependencies. How many of you have NPM dependencies that are like old or maybe deprecated, and you can't really upgrade a bunch of other things because you're stuck on this one version of something? Does anybody else have the problem? Yeah, about half the room, maybe a little more. So and one of the hardest parts of kind of being able to refactor, there's a pretty good prerequisite, which is having sufficient unit test coverage, right? If you don't have tests, you don't know what you broke, right? And so being able to even advocate for tests or being able to kind of explain to your product owners, why tests are important and, why tests are not secondary, they're actually really like first-class citizens. Like, there's a lot of cultural changes I think we need to make as engineers, when dealing with our non-technical stakeholders. But that said, being able to constantly iterate and refactor your code is something that you can do quickly. And I know that even when even having NPM dependencies, which are really like gigantic and kind of also exponentiate how much refactoring we have to do sometimes, like it's absolutely possible. And one of the reasons why it's actually we've kind of our bundle sizes have really gotten so big is we don't really think often enough when we're doing an npm install, like there's like a rent associated with the package, right? So are we really kind of thinking, hey, what is the cost of maintaining this package? Am I comfortable making changes? Am I comfortable contributing back to the maintainers if I find a bug? Right? There's a lot of questions around our dependencies that we don't think about, and they can be pretty burdensome. And so, how many of you guys, when like having to do a large-scale code change, use something like Regex? Or find and replace with your IDE, basically, which is Regex under the hood, right? So Regex is pretty horrible. Using Regex is kind of like this, like a cat trying to get something out of a bathtub. It's not precise. Can anyone tell me why? Like why Regex is kind of like actually is not good enough for like large-scale refactoring? You always make mistakes. Yes, that's one. Yeah. Synchronous? I'm not sure what you mean by that, but I'm going to be a good Samaritan and say okay. So, Yes, exactly. So the gentleman was like, you don't have context, right? You don't, if you want to change something, you don't really have contextual awareness. So Regex has a lot of limitations, like being really hard to use, right? So not developer friendly, that you don't have contextual awareness. And to be honest with you, like JavaScript is dynamic and regular expressions are regular. And there's an inherent conflict even just at that level, right? And I'll give you a good example of that. If you have like import, JavaScript import statements, are you guys familiar with ESM? Right, so you can say import foo as star, right? How would you catch that type of a rename with a regex, right? Even the most sophisticated capture group like wouldn't be able to do that. Additionally, if you have, you're trying to just change a function called, get property X, right? You can have like 10 classes that have that get property X, right? How do you know what context you're changing that function name in? And so regex is pretty limiting. And so I wonder, like, maybe like if there could only be, some technology that was, I don't know, dynamic and that could navigate our unregular code bases. Like, I wonder what. Can anyone take a guess? I don't know. No? And I have a spoiler alert for y'all because it's in the talk title. So we're going to talk about ASTs. So abstract syntax trees. So how many of you, let's take a quick poll because I, like many of you, I'm identify as a software engineer that writes code for the web. I'm not, at Boku we kind of flip between both platform and web developer land. But before I joined Boku, I was really primarily writing code for the web, and so. How many of you kind of have heard of ASTs or worked with ASTs before? Okay, fantastic. So, have you worked with ASTs as in terms of a compiler, or have you worked with them in terms of like a linting tool? I guess. How many of you guys have worked with ASTs for linting? Okay. How many of you have worked on ASTs in compiler land? Oh, fantastic. We have a few folks that are deep in compiler land. So. Let's take a look at what an abstract syntax tree is, and then we'll come back to some slides. All right, so can everybody see my screen? Is this big enough? All right, a little bit. So what you're seeing on the left, so this is a tool called ASTExplorer.net. It's like a fantastic tool for being able to work with ASTs and dynamically kind of iterate on whatever you're trying to do, whether it's build a linting tool, building a code transformation, or just trying to understand what a JavaScript snippet is trying to do. And so what you're seeing here is just some code, right? This is a standard variable declaration. And on the right, or I guess is this your left? I don't know. So that side, the gray side, what you're seeing here is this tree that gets generated. And so this tree is basically what gets fed to a JavaScript engine, right, that is parsing your code and trying to understand it. So it's like the it's the preparation for the machine to be able to take your high-level JavaScript code or Python code or Java code and take it down all the way to ones and zeros. And this little kind of preparatory step can be really useful for us because what we get is the standard output, the standard tree output, right? So everything is a top-level file, if you guys can see that, right? And then we have a program, right? So the file is like literally the context in which this is running. This is a program. Any comments that are above and below, right, would be there. And then you can see we have a body, right? And then we only have one thing in the body right now. And so if I take this and have like another variable, you can see we have another variable declaration. And so inside this variable declaration, we have the declarator, right? And then we have an identifier, And and in order, it's identifiers hello, right? So you're seeing here that we have these kind of like key token words that kind of are organized in this tree structure that we're able to kind of programmatically analyze, right? How many people think this is cool? Everybody, yeah? This is cool. So let's get back to the slides. So this is the official definition of an abstract syntax tree, right? In computer science, it's a tree representation of your code, right? And abstract syntax trees exist across all programming languages, and the real difference is in the tokens, right? And whatever structure is required for language X. There's in JavaScript right now. There's it's more or less an almost standard format for various parsers, and we'll get into what parsers are in just a second. But this is kind of, abstract syntax trees exist across all programming languages. So what we're going to try to briefly discuss today is what they are, how they're used, how they can be really helpful for refactoring, and we're going to get into a little bit about why they're better than Regex. And so I know the word compilers kind of scares people, but we're going to go ahead and take a look at some compiler architecture, and I promise it'll be really easy because they're just little boxes, so don't worry. And so when your code gets parsed by a JavaScript engine, right? So Chrome, the JavaScript engine is V8, also runs in Node. You can swap out your JavaScript engines in Node if you'd like to run Chakra, which is the JavaScript engine for Edge, right? So every browser kind of has their own JavaScript engine, and that's what parses our JavaScript code. And so the first step, is it goes through a lexer, and so lexers basically generate those tokens that we saw, right? Variable declarator, identifier, member expression, like what those things are. So we generate a set of lexical tokens, and then it goes through a parser, which takes those tokens and then outputs the tree. And that's kind of really where we stop for the case of what we're trying to do. And so it then goes through a translator, right, which translates everything down into bytecode, and we're going to hand wave over that. And so this is a great slide from Francesca Henkelman. She's an engineer on the V8 team. This is V8's process, right? So you can see that the kind of parsing of JavaScript, creating your lexical tokens, creating your tree, that's like a standard step for all of these engines. And the difference between the engines is really what happens in the optimization layer, right? And that's why some things are faster, or it's a step down from where we are. And so when we take our, we just take our JavaScript snippet of code, the first thing it does is create those tokens. So we can see here, we have keyword, right, equal, string, et cetera. And then this gets generated into that tree that we saw. Right. And so ASTs are actually part of the underlying technology that powers a lot of the modern tools that we use. Everything from ESLint to Babel to Istanbul, right? Being able to statically analyze your code. All of that is kind of really AST powered. And one of the main reasons why is because there's it's 100% predictable, right? And so how many of you guys use Babel? Almost everybody, yay, modern JavaScript. So just a quick shout out for Babel. Actually, Babel, it's not like a company or a big fancy engineering team that runs Babel. It's actually 100% volunteer run, and they have a Patreon. So if your company is interested in contributing to open source or giving back, please consider donating to that team. They're awesome. But Babel is a JavaScript compiler, and so unlike other compilers, it takes JavaScript as a source and then spits out JavaScript as a target, right? So JavaScript in, JavaScript out. And what happens in the middle is kind of run, it's dictated by a series of plugins, right? So if you run Babel without any plugins at all or any transforms, you just run it, it's literally going to spit out the same code that went in. And so let's look at how Babel works, right? So now that we know a little bit about how the compilers create ASTs, so first the code has to get parsed, right? And so it's kind of, there's kind of three architectures, right? We first parse, and then we transform, and we generate. So once we parse our source code, we generate a tree, and then the transform layer is kind of where all of the magic happens, right? So that's where we take tree 1, and we say, OK, tree 1, we're going to now start to query you, right? So using the visitor pattern, we can kind of traverse through these trees, right? It's just kind of standard breadth first search, depth first search, and we're able to say, OK, find me a node that has this property, find me a node that has this name, and now does it meet all of the conditions? OK, it does, great. Then run this change on it, right? And so we're able to kind of make these in-place changes that basically generate a new tree. And so now that new tree that gets generated after the transforms are run now needs to actually go get converted back into code, right? So we get this reverse process where we now have a tree that needs to go back into source code. And so voila, that's Babel. It's as simple as that. And Babel is so incredibly, I mean, just it's the concept and paradigm around Babel is so incredibly powerful that this is kind of one of my favorite Babel plugins that has kind of come out and really pushed the ecosystem. You know, can everybody see that code? Maybe it looks kind of tiny. I was hoping this would be a bigger screen. But basically, this is a plugin called preval. And so what this allows you to do is basically dynamically evaluate something at compile time. And then basically, whatever the value that gets evaluated is what gets outputted in your code, which means that like your code can literally be different every time you run Babel, as opposed to like, you know, like it can be different based on compile time. So an example, like a good example of this is like, imagine if you're like requiring in a bunch of files that are in your local file system, right? And that file list changes every time. So you're like, hey, I'm not going to make this like some like crazy process where I go fetch that, and you can do it dynamically by just saying, hey, preval this list of files, and it's a Babel plugin that'll basically return the right dynamic value. So this is pretty sick, and it's pretty awesome. And if folks have questions on this, like we can dive into that in a little. But so this is some of the really cool things that you can do with Babel. And so, like I said, those 3 steps are pretty much standard. So if you're interested in doing your own code modifications, these are the exact steps that you would follow, right? So you need to pick a parser, and there's various parsers, including Babel. JS CodeShift is the one that we're going to be looking at today. It's a wrapper around recast, and JS CodeShift is a project out of Facebook that just kind of gives you some nice jQuery-like APIs that let you query your code. And so once you have a parser, you're going to traverse your tree that gets output and make your in-place modifications, and then you generate out the transform code. And so the first time I learned about code transformations, which are really powerful, is in 2014. Adi Usmani, who I have a hard time like giving any talk and not bringing up Adi Usmani. So here's Adi Usmani. He basically wrote a code transformation for a JS hint, which is like a precursor to ESLint. And so you can see here this exact same workflow applies, right? So input source code, fix, so basically this kind of yellow box where you're like doing a transform is, getting the tree, getting the tokens, like making the transforms, regenerating the code, right? So like it's a pretty simple flow that has been kind of utilized by library authors for quite a while. And one of the reasons why it's really important as developers for us to really master this stuff is, it's important for us to create like resilient code bases, meaning, if we're, like I don't like having debates in PRs, pull requests. There's no point unless it's something. I don't like having debates around things that can be automated, right? And so we don't have to rely on just the rules that are in ESLint. You can write a bunch of your own custom rules, and you can use the same thing around bugs, right? So once you find a bug in your code and you fix it, you should think to yourself, hey, can I write a custom lint rule that will allow me to never get this bug again, right? Was it just some kind of JavaScript screw up? And if the answer is yes, great, write the rule, check it into your code. If the answer is no, then the next question you should ask yourself is, okay, can I write a unit test so that I won't ever get this bug again? And if the answer is no, then the next question should be, okay, can I write an integration test so that I never get this bug again, right? And so you can kind of follow these kind of three patterns to like, the patterns of defense, right, to kind of help build a resilient code base and squash bugs. So, all right, so let's look at JS code shift. So we're going to go back to AST Explorer. My screen is like huge now. Actually, I'm going to just open this and all right, so we're going to move this. And so if you guys are welcome to code along. I just wanted to show you how this works. If we're gonna just type in anything, we can go back to our, JS. We can write a const here, and so AST Explorer basically lets you pick your language stack, whatever. We're using JavaScript here. Over here, you have a list of parsers, right? So the main difference between these parsers is the core structure is all the same, but different parsers have different kind of helpers depending on like their own use cases, right? So like ESLint has their own parser, and they have a bunch of helpers that they add for themselves, when, same thing with Babel, et cetera. But the core structure is the same. There's just additional things in each of these parsers. So we're going to use recast. And if you want to run a transform, right, so if you want to actually write code that, if you want to be able to take the code and write something that will manipulate it, you can pick one of your transforms here. If you're writing an ESLint rule, so when you guys are familiar with the -- fix in ESLint, right? If you want to automate that, that's actually AST powered, right? So we're going to use JS code shift. I think it's the simplest API, and you can see here what gets spit out. Can you guys read that? Okay. Sorry, it's a tiny screen. So here we have, so JS code shift basically has its own little API, but we have our file, and we're able to we get these really nice functional style methods that we can chain, which is awesome. And so here we're looking for an identifier, right, which is what we looked at. And what we're doing with that identifier is we don't have a filter on it, right? Like we're just looking at any identifiers, and we'll add a filter in just a second. But what we're saying is for anything that has an identifier, I want to now, we're iterating over all of the things that we find, and we're saying, hey, take the identifier and replace it with a reversed and like basically a backwards, like, you know, like flip the values, right? And so you can see here we have like an uppercase I identifier and a lowercase I identifier. Can anyone tell me what the difference here is? Does anyone can take a guess? Pardon? One is a property, one is a method. Not exactly. Anyone else? So basically, this uppercase identifier is really referring to the wider token, and what we're doing here with the lowercase identifiers, we're building code, right? So if we're basically able to build code in addition to just manipulate it, which is awesome. So we're literally building a string here that, you know, we're taking the value of this path node and we're replacing it. So if you look to the right here, our hello.js is now OLA JS, right? And so that's our identifier. And so you can now take this same, you know, formula here and do whatever you want, right? So we can add a filter to say, I only want to manipulate variables that are hello. So let's do that together. Live coding is so fun, right? So so how would we figure this out? So we're gonna look at identifier. We're gonna try to, I'm gonna collapse this for a second. We're gonna try to find this tree structure, right? And so the really cool thing about all of this is you don't, so we have an identifier and we can see that, you know, its name is hello, right? So, okay, cool. So if we go back to our code, is there a bug in this? Oh, sorry. Yeah, so if we go back to our code, we can now add a filter here. So we're finding identifiers that have the name hello. So I now only want to manipulate ones that have hello, right? So now if I have another variable that's, you know, hello moto JS, you know, you can see that we don't right, like the other one didn't get manipulated, right? So we're querying for something that's specific, as simple as, you know, just the name of a variable, and we're saying do something with it. And so we can get really, really, really sophisticated and very, very advanced with all of these changes. Meaning, you know, I can say, you know, find me, you know, I have something that I'm importing from import foo as star, right? That's dynamic. So we can write something that makes sure that what we're changing is correct based on the, you know, module name that in the string component, right? So we can be very precise with our changes in a way that really we can't do with Regex. Like, it's pretty cool. So yeah, so basically ASTs are awesome. I highly recommend all of you learn them and dive into them. You know, we don't have a ton of time to like really get into the like nitty gritty, but I'm here for questions, and I'm going to share my slides and some additional resources for you guys to start playing around. But basically, the ABCs of ASTs, that they're awesome, awesome, awesome. And you know, I want to say thank you so much. So I'm at Nomad Techie on Twitter. I podcast on the Web Platform Podcast. It's a pretty JavaScript and web-based podcast, and I work at Baku. So that's it. Thank you all.